Yeah.
Okay,
right.
hit it.
Hit it?
Yeah, I did.
Okay, everybody. So let's talk. Everybody, give me your attention. We're going to be calculating the efficiency of the hot pot. When you calculate the percent efficiency of anything, you are going to compare the useful energy output to the amount of energy you put in. If it was a 100% efficient situation, these would be exactly the same. But usually, which is going to be larger, the energy you put in or the energy you get out in any system?
The energy you put in.
That's right. The energy you put in is going to be larger, and because of the second law of thermodynamics, you're going to get less useful energy output. And this is the example. So you start out with 500 milliliters of water in the hot pot. Let's say it's at 20 degrees Celsius. And you plug it into the wall. Electricity flows through. That causes these coils to heat up. That heat transfers to the water. And then, and obviously, the temperature of the water is going to go up. And you're going to heat the water until it gets to 80 degrees Celsius. That is your energy output. So the electricity is your energy input, and hot water is your useful energy output. Which, so okay, what units do we use to measure the electricity?
Watts.
Watts or watt hours. And what unit are we going to use to measure the energy that we put into the system here? Right, calories are what you use to measure temperature change in water 1 milliliter at a time. If this was pounds of water, we could do it directly into British thermal units. We could probably manage that too, but we're going to do calories today. Useful energy output measured in calories. Right. And so, well, we have calories and we have watt hours. Can we make them meet? Can they meet somewhere? Is there one way to convert one into the other? Is there a unit that you can convert both of these into? There is. I'll tell you what. Look on page 99 of your book if you have your book handy and look and see. Is there a conversion? Is there something that calories and watt hours, both of them, can convert into?
What, 99? BT?
99. BTUs, that's right. British thermal units. BTU. Right. And in other words, watt hours and BTUs can be correlated by, I believe it's 3.413 BTU. Oh, that's not very neat. 3.413 British thermal units equals 1 watt hour. So that's one. So if I can get calories to BTUs, then I can get from BTUs to watt hours. Sorry. And we can also convert from calories to BTUs using the conversion 252 calories equals 1 British thermal a unit. So, alright, so we're going to be able to do that. And take a minute and write that down, and I'll tell you what, you can hit the red button there, and I'll give you. Are you ready? We're rolling?
Yep.
Okay. All right, everybody, we're back, and now we, if I could just step over here for just 1 second. We talked about what we need. We need our useful energy output, which is the hot water, divided by our energy input, which is the electricity, times 100% actually. Here it is over here. In order to get this, we have to go through a few calculations. And so this is how we're going to do this. How do we calculate each of these things? The top, the numerator, useful energy output, is basically the heat that goes into the water. And the energy input is the amount of electricity that goes into the system. So the first thing I'll remind you how to do is how we do the useful energy output, which is how many calories the water absorbs, the water takes on. And it's really not that hard. remember how we do these, how we did these when we practiced them, was the milliliters of water times the change in temperature. And so in this case, how many milliliters of water do we have? 500 times, what's our, let's say, okay, yeah, from 20 degrees to 80 degrees, our change in temperature is 60 degrees. Oops. And so, does anybody have a calculator handy?
I have my phone.
You may use your phone.
$30,000, $3,000, $30,000.
How'd you do it?
30,000. Oh yeah, look at that. Actually, it's a nice round number.
You can't do it either.
The number is 30,000. 30,000 what? Calories, right. 30,000 calories. Sorry if the writing is small for our viewers at home. So we have 30,000 calories, which is not watts, and so we have to convert this. So the point is, you're going to do this when you take your data in a little bit. You're going to measure the temperature, and you're going to figure out the amount of calories from there. Because room temperature is actually slightly off from 20. It's usually between 20 and 24 degrees. You're going to go up to 80 degrees. You're going to calculate the number of calories, and then you're going to convert it to BTUs. So let's do that. Calories to BTUs. Okay. Well, actually, I'm not going to use this horrible green marker because it doesn't look like it's going to work well. Let's just use black. So if our conversion factor is that 252 calories equals 1 BTU, then all we have to do is do what? We take our calories. What do we do with that number of calories?
Divide into 30,000.
Divide what into 30,000?
252.
That's right.
30,000.
So we divide 252 into 30,000, or put it to draw this in a more sciencey way. Well, that's fine. We'll just do this. 30,000 divided by 252 calories per BTU is going to give us, does somebody have that number for me yet?
119.04.
We'll just call it 119. 119 BTU. Okay, that's good. Now we're getting closer. Now all we have to do is do BTU to watt hours using the conversion 3.413 BTU equals 1 watt hour. Okay, let me move this line. It's not low enough. So, okay, again, same thing. You're just going to take your 119 BTUs and you're going to divide it by 3.413 BTUs per watt hour. And what do we get when we do that? Anybody? Anybody?
What is it?
3.413. So, in other words, if 3.4 of these make 1 watt hour, you divide
34.86.
34 point, we'll call it 34.9 watt hours. And so that's our answer for useful energy output. .9 watt hours. So in this calculation, that's going to go up here. 34.9 watt hours. Your numbers will be slightly different. I'm just showing that's how we get the part that goes on top.